Okay, hello everyone. Welcome to today's lecture. Sorry, I was not able to do the lecture of last Thursday. Uh, so we had to skip the day. Uh, I don't think that it will affect our schedule in the sense that we will still be able to cover all the planned material, hopefully. Okay, so uh, I have shared my screen and I think slides are visible to you. If not, let me know, okay? So last time we were talking about analog to digital conversion in AVR. We have almost covered the topic, but we were not able to cover the example. So we will start today from the same place where we left last time, and we will have a look at example, and after that we will also talk a little bit about digital to analog conversion. Okay, so let's first have a look at the example. uh, Remember your lab 6, I think lab 6, yeah, which is due next this Thursday, I guess. It is also about analog to digital conversion. Basically it is this example with slight changes, right? So, what you need to do in this example is that you need to read analog input from a potentiometer, which is connected with ADC0 or analog 0 pin of your microcontroller, and then display whatever analog input you need to display it on the digital as digital output on 10 LEDs, and those 10 LEDs are connected with port D and port B. So the lower 8 bits are connected with port D, and remaining higher two most significant bits, they are connected with the port B at pin location 0 and 1 of port B, right? And the output of the ADC is right adjusted. Remember, we said that the output of ADC is 10 bits and it is contained in two registers, ADC low and ADC high. And when we say right adjusted, it's mean that the eight least significant bits are contained in ADCL, and two most significant bits, they are the bit 0 and bit 1 in ADCH, and most significant 6 bits of the ADCH, they are empty or they are not used, right? So this is how your hardware interface will look like. So here basically you have wait a minute. So here basically you have a potentiometer connected at ADC 0. So potentiometer is simply it acts as a variable resistor, and as a result of this variable resistor, you can have variable voltage coming out of the potentiometer depending upon what level of resistance you have plugged in. So in this example, you need to use the internal V reference of 1.1, and you need to set the ADC prescaler to 1 by 128. So you basically what you are doing is that you are dividing the source clock by 128 and then feeding it to the uh, ADC unit of your microcontroller. And also you need to use the polling mode to detect completion of conversion, which means that you are not using interrupt mode. Remember last time we talked about that you can once your conversion is completed of an analog signal into digital form, after that a flag is set, which is ADIF flag, right? So, but then once the data is ready in digital form, we need to do something with that data, right? For example, read it from those ADCL and ADCH register, put them somewhere, right? So that those registers, they are available for the conversion. But there are two ways to do that. I mean, to handle the output. Either you can do it manually, which means you are using the polling mode. You continuously monitor the ADIF flag, and once it is one, only then you go ahead and read the data out from ADCL and ADCH register. And the other option is that you don't monitor the ADIF flag, you enable the interrupts and you write an interrupt service routine. So whenever the conversion is completed, an interrupt is raised, and when the interrupt is raised, your interrupt service routine is executed, which you have already written and put in the memory. But we didn't have a look on how to do that because we have not covered the interrupts, so we want to just confine ourselves to the polling mode. Any questions before I go toward uh, solution code? Any confusion in like the description of example itself? No? Okay. So here actually I am not going to write the code. I mean the code is already in the slides, but I want you to write the code, or at least give it a try, right? So first thing is like you need to configure both port B and D in output port, right? Because I want to connect LEDs on these ports. So I'm releasing this poll. You can go ahead and try to do this question. Mm, week 10, day 1 quiz 1. Yeah, this one, right? Okay. Yeah, you have 60 seconds to try this one. Okay, giving you 30 more seconds. Okay. So it is straightforward. You have done this so many times in your labs, right? So you are simply loading 0xFF in R16 and sending R16 to DDRB and DDRD. And in this way, both the ports are in output mode, right? The next thing you need to do is you need to disable the digital input buffers on ADC pins, right? Where are the ADC pins? So ADC pins are on the port A, right? Remember, we talked about this register DIDR0, right? Uh, so you need to disable all the input buffers, and how you disable by writing 1 to that register. So I am releasing this poll. Go ahead and uh, try to do it. Week 10, this one. And yeah, you have 60 seconds. I will not increase the time because otherwise we will not be able to complete the lecture. Okay. So again, it was straightforward. You just need to do what? You need to write all ones in DIDR0. And how you can do that? By simply writing sending R16 to DIDR0. Remember, R16 already has 0xFF, right? So you don't need to do anything else. Just write R16 DIDR0. Next thing, you need to select, remember, you can do this by writing ADMUX register. Uh, so maybe you can open the lecture slides from the previous lecture where we discussed about ADMUX, and you can look at the ADMUX register and then set the value such that ADC0 is selected as an analog input, V reference is selected as the internal 1.1 voltage, internal VREF of 1.1 volt, and the result of a 10-bit result of ADC conversion is write justified. So basically, you just need to write correct value in the ADMUX to achieve these three features, right? So again, we are releasing the poll. Try to do this. You have 120 seconds. If you have question, you can ask me, okay? I mean, uh, about the lecture, for example, why we were writing 0xFF in DIDR0 or something. If you have any question, you can stop me. Okay, please everyone try to participate in these polls. Even like if you think your answer is not correct, still try to solve them. Okay, because the percentage participation percentage is like very low, only 37%, which is not a good thing, right? So okay, so how can you do that? By writing 0xC0. So when you into ADMUX register. So why 0xC0? When you convert it into the binary, what will be the binary of 0xC0? 1, 1, 0, 0, and then four zeros, right? So if you remember ADMUX, uh, last the five least significant bits, they are used to select the analog input. And if you refer to that table, which we have seen in the previous lecture, if all these bits are zero, it's mean you are selecting ADC0 as input, analog input, right? The most significant bit, uh, it is mm, yeah, I need to again. I think I need to refer the lecture slides because I don't remember the mm, internal bits of the register, right? And I don't expect any one of you to also remember, right? So here, uh, so this is the ADMUX register. So the most two significant bits, they are used to select the reference voltage. So when you write 1, 1, it's mean you are selecting internal 1.1 volt. And the ADLR bit, when it is 0, it's mean your output will be write justified, right? So uh, that's why you can see my screen, right? If not, send me a message. So that's why here we were writing 0xC00, right? Let's move to the next step, which is now we need to enable the ADC, analog to digital conversion unit, set the prescaler equal to 128 and polling mode, and we want to use the polling mode, right? So for doing that, we need to write which register, ADC SLR register, right? And for making the to enable the ADC, we set the most significant bit equal to 1. For a prescaler equal to 128, we set the least three significant bits equal to 1 and everything else is equal to 0, right? So go ahead and actually already I have given you the solution verbally. So go ahead and do the polling quiz 4. Okay, giving you 30 seconds more. Okay, so we are writing 0x87 in ADCSRA through R16, right? So why? 0x87, when you convert it to binary, it is 1, 0, 0, 0, and then 0, and then triple one, right? So these three triple ones, least significant bit, they actually used to specify the prescaler. So when all three bits are 1, it's mean you want to use prescaler of 128. Most significant bit is to enable the ADC, and everything else is 0. Why? Because this is the fourth bit, which is, I guess, used to specify the polling mode, whether you want to enable the interrupt or not. So if you don't want to enable interrupt, you keep the bit 0, right? And we said we want to use in this example the polling mode. Another thing, we said that all these ADC related registers, you cannot access them using IO instructions like in and out. That's why what we are doing is that we are first writing the value, whatever we want to write in, we are putting the value in R16, and then we are saying uh, store to the static memory. We are using STS instruction to write R16 into ADMUX or R16 into ADCSRA. Okay, let's go to the next step. What we need to do now, we have enabled the ADC, and now we need to start the conversion. How we start the conversion? By making the seventh bit of ADC 1, right? So what we need to do is that we need to write a couple of lines which basically start the conversion, and then uh, uh, by setting the bit 1. Okay, so I am, and keep in mind, you cannot use the IO instructions, which mean you cannot even use SBI instruction like a set IO bit, because that is used for IO register, and ADCSRA is not IO register. I mean, it is the IO register, but in the extended field, or it is the extended IO register. So we cannot use the SBI instruction with ADSRA register, right? So how can we set only the bit at index number 6 in the ADCSRA register? By doing what? OR operation, right? So I have given you hints now, and I'm releasing the poll and try to do that, okay? Uh, you need to set only the bit at index 6 in ADCSR register to 1. Keep all other bits as they are. Don't touch them. But you cannot use the IO instructions like SPI. You have 30 more seconds. 30 seconds left. Okay, so let's see how to do that. What we are doing is that we can first read the ADCS register into any general purpose register like R16, and then we are saying that shift 1 to the towards left, how many times? ADSC times. What is ADSC is 6. So basically I'm doing nothing. I'm just first saying that shift 1 towards left 6 times, right? So what is 1? What is the 8-bit binary of 1? 1. It is 0, 0, 0, 0, 0, 0, 0, and 1, right? This is 8-bit binary of 1. Now when I will shift this one left 6 times, what will I get? So this one will be moved into the bit position number 6. Yeah, I mean, I don't want to do, I don't want to write the number after shifting every time toward the left. So I'm writing the final result after shifting 6 times toward the left. So 1 will be in this position, right? Right? So basically I'm saying R immediate R16 with this number, this binary number, right? So if you are do R immediate operation with any 8-bit number, like let's say I don't care 8-bit number, I don't care what the values are, right? So whatever values are, I will get what will be the output. All other bits will retain their values, but I'm sure that the bit at number index 6 will be 1, and all other bits will have whatever value they had uh, in the ADCSR register. So basically I'm just setting the 6th bit at index 6 of the ADCSR, right? Is everyone with me on that? I don't understand. Okay. Okay. So if you don't understand, then let me go to the to OneNote. What is the less than symbol for? Okay, I will explain. Wait. Let me go to OneNote. So week 10, day 1, right? So let me quickly copy the code snippet. So this was the code snippet, right? So here, what I'm saying. So in this line, I'm saying put the value of ADSRA in R16, right? So in R16, I have the value, right? Remember in the previous step, what we did, we set the most significant bit equal to 1. We set all other bits equal to 0, and we set the least three significant, at least three LSBs equal to 1, right? And all other bits are 0. Is everyone with me until this point? If not, send me the message. Okay. Okay. So, okay. And then in the next, what we are doing, we have not yet covered this statement earlier. Actually, we were going to cover it today, but anyway, I have included it in the solution. So what is the purpose of, what is the meaning of this expression? 1 ADSC. ADSC actually, I have explained, I have defined ADSC here in equate. What is ADSC? ADSC is 6, right? So effectively, I'm saying uh, I have this expression 1 less than 6. So what does it mean? This less than means shift left. Shift left. Shift left what? Shift left 1. Okay, so I'm going to shift left 1. How many times? I'm going to shift it 6 times. So let me do it in binary form. So when I write 1 in 8-bit binary, it will be 0, 0, 0, 0, 0, 0, 0, 1. Now let me shift it 1 time to the left, right? So I'm just writing here 1 to indicate that I'm shifting it 1 time. So when I will shift 1 time here, what to the left, what will happen? I will have a 0 here. 1 will move to the next position. 0, 0, 0, 0, 0, 0. Everyone with me? After second shift left operation, it will be 0. Everything will be shifted once towards the left. 1, 0, 0, 0, 0, 0, right? And so on. So after sixth left operation, you will have 0, 1, 0, 0, 0, 1, oh, sorry, 0, 0, 0. So you will have this thing in R16, right? So this is R16 here. Now in next statement, sorry, so not in one, sorry, you will not have this in R16, my mistake. So this is a result of, this is the result of 1 ADC, right? ADSC. So this is the immediate number you will have in this instruction. You are saying OR R16 with this immediate number. What is R16? R16 is this one here, which contain the value of ADSCRA. So what is the immediate number? This one. I'm putting it there. 0, 1, 0, 0, 0, 0, 0, 0. So when you will do immediate R, when you do R, so what will be the result? 1, 1, 1, 0, 0, 0, 1, 1. So what is the difference? This bit is set now, right? But it is in R16. So this result is in R16, right? And then you are saying in the next instruction here that put this value in the ADC-SRA register. So now this value will also be the value of ADC-SRA register, right? Everyone is clear on this? So yeah, that's correct. So someone asked that, so would like to right arrows also shift to the right? Yes, that's correct. We will cover those instructions, though these are known as directives. We will cover them today, okay, in upcoming slides. So having said that, I can move forward, right? If you change them 1 to 2, would that shift? Yeah, that's correct. Someone asked that, would you change then 1 to 2, would that shift to the left? Yes. Okay, I'm assuming now it's safe to go back to the lecture slides. Okay, so after starting conversion, remember what we need to do. After starting conversion in ADC, we need to monitor the ADC completion flag, right? Interrupt flag actually. So we need to monitor that. So when does that flag become one? It becomes one when the completion is when the conversion is completed, right? And otherwise it stays zero. So what we need to do, we need to wait until the conversion is complete, which means we continuously monitor the ADIF flag in the ADCSRA register, right? And if it is not one, then we keep checking it, and if it is one, then we proceed with the remaining of our program. We move to the next instruction in our program, right? So before I release this next poll, let me take you to the this uh, slide again to show you the ADCSR register internal bits. So here, AD enable, ADSC, ADDate, ADIF. So you need to monitor this bit, right? So which is bit number 4 of the register ADCSRA. Clear? So you need to monitor the bit number 4 of ADCSRA register. Okay. So with this information, I'm releasing the next poll. Go and try to attempt it. Try to write the answer. Okay, you have 120 seconds. Remember, we cannot use IO instructions like SBIS. We cannot use that instruction, right? Okay, so let's go back. So how we can do that? By first, what we are doing is we need to monitor the, as I said, bit number 4 of the ADCSR register. So first we are putting ADCSA in R16, right? And then what we are doing is we are doing and immediate operation, right? Again, what is meaning of this one? This I have defined ADIF equal to 4, right? So I'm first saying shift 1 to the left direction 4 times, right? I don't want to go back to the one note here, but I can try to explain on the slides. So I have 0, 0, 0, 1, right? So I have one 8-bit binary of 1, and then I'm saying shift it uh, left 4 times, right? So when I will shift it for left 4 times, what will I get? I will get a 1 here, and all other bits will be zeros. So bit at index 4 will be 1, right? And all other bits will be 0, right? And then I'm saying do the AND operation between R16 and this number, right? What is R16? R16 is the value of ADC-SRA, right? So I don't care about other bits of ADC-SRA. I care only about the uh, bit number, at index 4, right? So I'm just writing B to indicate that, right? And all other bits are, I don't care. So I don't want to write X for the meaning of them. So what will be the result when you will use bitwise AND? So because one of the operand is 0 here, so the least significant 4 bits will be 0 anyways. The most significant 3 bits, they will be also 0 because see here, if one of the operand is 0. What about the bit at index 4? It will be 1 or 0 depending upon what? Depending upon this actual bit value. If this bit value B is 0, the result will be 0. If bit value is 1, then the result will be 1, right? Let's say that this ADIF flag, so the conversion is completed and ADIF flag will be set equal to 1 by the hardware. So if it will set equal to 1, result will be what? This one, right? So which will be like non-zero result. So in next instruction, I'm saying, okay, now check branch if equal. Remember what does the branch if branch equal instruction does? It checks that if the Z flag is equal to 1 or not. When is Z flag is equal to 1? When the result of operation is 0. But our result of operation is not 0. So Z is equal to 0. The flag is not 1, right? So we will not go back, right? We will not go back, right? However, if the conversion was not completed, then this B bit, it would have its value of 0. So as a result, the result of AND immediate operation will be 0 here, and Z flag will be equal to 1, not 0. And in that case, we will go back to the loop and we'll keep going back until this conversion is completed and the bit flag is set equal to 1, right? Any questions here? Any questions? No? Okay. If not, then let's go to the next step, which is so once our conversion is complete in the previous slide here, conversion is complete, then what will happen? We will not go back in the loop. We will actually, the control will go to the next instruction. What is the next instruction? We want to read the low byte. Okay. So I'm not releasing this next poll because it is straightforward and we are running short on time. So you are basically simply reading the value of ADCL into R16 and then sending that value through R16 to port D, right? So remember, we must first read the low byte and then after that we read the high byte, right? So you read the value from ADCH into R16 using LDS instruction, and then you send R16 to port B, right? And but here now comes the important part. So remember, one conversion has completed. But what we want to do, we want to continuously read the analog signal from the potentiometer, which is connected on the ADC0, convert it into digital form and display on the LEDs. So we have done it once, but remember the ADIF flag was set equal to 1 because conversion was completed. So in order to start the next conversion, we need to set that ADIF flag equal to 0, right? And how we set that ADI flag? Okay, let me go back to the slides of the previous lecture again. So remember, this flag is set equal to 1 once the conversion is completed. But we want to also read the analog signal again and again convert it into the digital form, right? But in order to do that, if this bit was set equal to 1, we need to manually need to set equal to 0. And here is the tricky point. In order to set it equal to 0, you have to write 1 to it, not 0 to it. you have to write 1 into bit number 4 of the ADC SRA register, right? And this is what we are going to do in the last step. So reset the ADIF to 0 by writing 1, to ADIF, not 0, okay? Again, I'm not releasing the poll. So what I'm doing is that I'm first reading the ADCSR register into R16, and then I'm saying R immediate R16 0 bit 000 0 bit binary 0001 000. I did it in binary form this time just to make it more clear, right? Otherwise, you can also do 1 shift left 4 times. So here you are saying actually that uh, read the original value of content of ADSRA in R16, do R immediate operation with this binary value where you are setting the bit number 4 to 1, and then you are saying now write back the value of R16 into ADCSRA, right? So when you will write back, you are making sure that the bit at index 4 will be set equal to 1, which will actually, the hardware will then set it equal to 0. Any questions? Any questions? No? Okay. And then after that, you need to repeat forever. So what you do is that you are simply jumping back to read ADC1. And what is ADC1? It was just a label uh, here. Read ADC1. You just jump back here. So again, you will start again the conversion. You will then wait until the conversion is complete. You will again read the low byte ADCL. You will read the high byte. You will again reset the ADI flag to 0. And again, you will jump. Okay. Any questions? Okay. So this was our example. And again, your lab 6 is like uh, just a slightly modified version of this example. Okay, signal conditioning. What is signal conditioning? So actually, about before answering that, let's first talk about transducers. Transducers are sensors. These are the devices which actually convert your physical data, for example, temperature, pressure, light intensity, velocity, etc., to electrical signals, right? For example, capacitance, resistance, current, or voltage. So signal conditioning is the step that changes these signals to the voltage for conversion. For example, if there is a sensor which is converting a physical data into an electrical signal, for example, let's say it is converting the temperature into capacitance, or temperature into resistance, or light intensity into current. So we cannot feed that electrical signal, for example, capacitance or current, as an input, analog input to the ADC, because ADC accepts only voltage signal as an input. So we need to convert that those other electrical signals into equivalent voltage, right? And this process is known as signal conditioning. We are not going to see how it is done because again, we are computer engineers, we are not electrical engineer, we are computer scientists, not engineers, you know. So, and we are not taking a course on electrical engineering, so we will not go in that direction, but you just need to remember or know what signal conditioning mean. So in analog world, everything is like all the physical data is in analog form, like temperature, pressure, etc. Then you use a device like transducers or sensors to convert those physical quantities into the electrical signals. And then that electrical signal need to be converted into the voltage. And once it is converted into the voltage through signal conditioning, you feed it into the ADC, and then ADC will convert that analog voltage into the digital form, which will then be processed by your microcontroller. In our case, ADC and microcontroller, though both are on the single chip. So we have this thing in a single chip. Okay. Okay. So let's do then our quiz 10. Okay. You have 30 seconds. Hmm. Okay, so correct answer is that signal conditioning converts an electrical signal to voltage. And it's interesting. I see like 60% of the participants said that gave the correct answer, but then 47% of the participants selected that signal conditioning converts physical data to electrical signal. No, that's not correct, right? Because signal conditioning mean you are converting an electrical signal to the voltage form, right? Okay, let's go to next slide, temperature sensors. So actually there are two type of temperature sensors. Ones which are known as thermistor. They actually change the resistance with temperature. So basically, as you increase or decrease the ambient temperature, these sensors they are actually resistors, and their resistance is dependent upon the ambient temperature. As the temperature increases or decreases, their resistance changes accordingly. And since resistance is an electrical signal, so it's mean we have a device which is working as a sensor, and then we can convert that resistance into the voltage form, right, by simply running a current through it. Thermocouple is also a sensor, but the difference is that it also measures temperature, but it measures temperature as a voltage. So if you increase the temperature, the voltage generated by a thermocouple sensor, that voltage will increase. If you reduce the temperature of the environment, the voltage produced by thermocouple sensor will reduce, right? So you don't need to actually do conversion manually. The single chip, there is a single chip which is actually already giving you output in the form of voltage. So you don't need to do signal conditioning. But if you are using thermistor, so then you need to first do the signal conditioning on the output of the thermistor, and after applying the signal conditioning, which means converting the resistance into the voltage, then you apply that voltage as input to the analog to digital converter. So there are like two popular IC sensors, temperature sensors, LM34. So it is a temperature sensor which will output voltage, and that voltage will be linearly proportional to the ambient temperature in Fahrenheit, right? So for example, if your ambient temperature is, let's say, 0 Fahrenheit, the output of the sensor will be 0 millivolt. But let's say if the temperature increases by 1 degree, like it becomes 1 Fahrenheit, the output will be 10 millivolt. So if the, let's say, temperature increases to 2 Fahrenheit, the output will become 20 millivolts. So for every degree of Fahrenheit, the output increases by 10 millivolt. So the step size of the sensor is 10 millivolt. You also have LM35, which does exactly the same thing as LM34, with the difference that its output it measures the ambient temperature in Celsius. So what does it do is that its output is also in voltage, but the output voltage is linearly proportional to Celsius temperature, not Fahrenheit temperature. So again, using the same example, if let's say the ambient temperature is 0 Celsius, so the output will be 0 millivolt. But when the temperature it rises to 1 degree Celsius, so the output will be 10 millivolt uh, for the sensor. And it is simply a three-leg device. So one is like your ground, the other is like your VCC or power supply, and the middle pin is your output voltage, which is dependent upon the environmental temperature. Any questions? Okay, so then let's go to the quiz number 11. Go ahead. You have 30 seconds. Okay, you have 30 more seconds. Okay. So the first statement is correct. Thermistor converts temperature into resistance. That is correct. Second statement is incorrect. Thermocouple converts temperature into current. No, thermocouple converts temperature into voltage, not current. Third statement is also correct. Thermocouple converts temperature into electrical signal. That's correct. Thermocouple converts temperature into voltage, and voltage is an electrical signal, right? And thermistor converts temperature into voltage. That is wrong because thermistor converts temperature into resistance, not into voltage. Okay, let's go ahead. So this is just a diagram to show how you can interface a temperature sensor with your microcontroller. So you have, like, let's say LM35 or LM34, both of them are three-leg device. It is simply an IC. So as I said, one of the outer leg is ground, the other outer leg is VCC, and the middle leg you connected with any one of the analog input of the microcontroller, for example, ADC0. Okay. So now here is an issue. The issue is that there is mismatch between sensor output and ADC range. What does it mean? Let me try to explain. Suppose that you have an ATmega328P microcontroller and its reference voltage is equal to VCC, which is 5 volt, right? So a number of output ADC bits on this microcontroller we know is 10 bit. So it is 10 bit ADC. So what will be the step size? 5 divided by 2 raised to power 10, which is 1024. So step size will be 4.88 millivolt, right? So this is the step size of your ADC, right? So if you if you want to visualize it, so you will see, like, if you have zero input voltage, the output, digital output, will be zero. If the input is 4.88 or close to 4.88, again, if there is something in middle, you will definitely have an error. But if you have input of 4.88, so output will be 1 in digital form. I didn't write a 10-bit binary of 1 because it will take space, right? And if your value is like analog input is 9.76 millivolt, the output will be digital output will be 10-bit binary of 2, and so on. And maximum is like when you have 4992 millivolt, your output will be 1023, not 1024. Sorry, my mistake. So it should be 1023, right? So this is your, on like bottom side we have input analog voltage, and on the top side we have 10-bit ADC output in the decimal form, right? Now, and this is the step size. Now let's have a look at the sensor. So for example, let's say we talk about LM34, right? So the range of the operational range of LM34 is actually -50 to 300 Fahrenheit, but practically it can work from 0 to 300 Fahrenheit because uh, okay, let me not give you the reason why we are not covering here minus negative Fahrenheit or negative temperature, because then we need to talk about negative supply voltage, and then it will take our time, and it is not a concern for us, so I don't want to waste time. Okay, so uh, let's say we focus only on the positive range, like from 0 to 300 Fahrenheit, right? So, so you will have, like, on this line, I'm drawing the Fahrenheit after every 1 degree, like 0, 1 Fahrenheit, 2 Fahrenheit, and maximum is 300 Fahrenheit, right? So the sensor will output you, give you the zero voltage, zero millivolt, right? When you have 0 Fahrenheit. When the temperature is 1 Fahrenheit, the output will be 10 millivolt, right? And when the temperature is 2 Fahrenheit, the output will be 20 millivolt. And when the temperature is maximum, like 300 Fahrenheit, the output of the sensor will be 3000 millivolt, which is basically 3 volt, right? So what is the step size of the sensor? Step size of the sensor is 10 millivolt, right? Now, again, this is just I'm trying to explain. So they, on the downside we have ambient temperature, and on the upper side we have the sensor output, right? Now, sorry, let me discard these annotations. Okay, now let's say that that's sensor LM34, and the environmental or the ambient temperature is 1 Fahrenheit. So if the ambient temperature is 1 Fahrenheit, how much voltage will be produced by the sensor? 10 millivolt, right? So, and then we will feed that 10 millivolt to what? To input of the ADC, right? So if now we look at the upper line, so if we feed 10, 10 is the like closest value to 9.76, right? On the scale of the ADC, right? So 10 will be treated as 9.76 millivolt. So when the input analog signal is 9.76 millivolt, what will be generated as output in the digital form by the ADC? 2, right? So basically what is happening here? So ADC is telling us that the environmental temperature is 2 Fahrenheit, but this is not true. Why? Because we know that the environmental temperature is 1, right? Sensor is, and then sensor is generating 10 millivolt. But when that is fed into the ADC, ADC converts it into 2, right? So there is mismatch. What do you mean? What do we mean by mismatch? Because mismatch is coming because of the fact that both have different step sizes. Like our sensor and our ADC ADC unit, they have different step size, right? So it is actually we expect that our ADC should tell us that the output should be 1, that the temperature is 1 in digital form, it should tell us, but it is actually telling us 2. So how can we fix it? By finding the scalar factor and then scaling our output using that factor. How can we find the scaling factor? By dividing ADC step size by the sensor step size, right? What is ADC step size? 4.88 here. And what is the step size of the sensor? 10 millivolt. So 4.8 divided by 10 is 0.488. So now we need to scale the output of ADC by scaling factor, that is 0.488, right? So which means we simply multiply this digital output with the scaling factor. So when you will multiply, you will get 0.976 Fahrenheit. So which will be almost equal to 1 Fahrenheit. Okay. So now your result will be correct, because now after scaling, your system or your device, your microcontroller will be telling you that temperature is 1 Fahrenheit, which is close to the actual temperature, environmental temperature. But if you don't do the scaling, your ADC will giving you the false output. And that false out is basically stemming from the fact that the step size is different for both for the sensor and the ADC device, right? Any questions? Do you have any question? No? Okay. If no question, then let's go to the quiz number 12. Okay. So you just need to assume that ADC is 12-bit. Everything else is same as in this example, which I just explained. If that is the case, if ADC is 12-bit, not 10-bit, then what will be the scaling factor? Okay, I think I can go ahead and uh, show you the solution. It is straightforward, right? So how it is straightforward, you first need to calculate the step size of the of the ADC. So basically you are simply dividing 5 with 2 raised to power 12, which is 4096. So when you will divide with 4096, you will get the new step size, right? So once you have new step size for ADC, you will simply plug it in here. Everything else will be same, right? So when you will plug it there, so you will get the scaling factor of 0.122. Okay. Okay, so we have talked about analog to digital conversion. So reverse, we also need to do sometime the reverse separation, which is digital to analog conversion, right? So why we need to do digital to analog conversion? Because uh, s- so if this is your ADC, right? So remember why we wanted to do analog to digital conversion, because we say that whatever, if we want to read an analog input from like real world or the world around the around the microcontroller, so that word is analog, so you first need to convert it into the digital form. In the same way, if we want to control the digital world, analog world, through our microcontroller, the signals generated by the microcontroller, they are in digital form, right? So we need to then first convert that output which is generated by the microcontroller into the analog form. So here is, I can give you an example. Like for example, let's say you have an output pin like PB0, right? So what values you can write on as output on the PB0? Either 0 or 1 in logical form, right? Like logic 0 or logic 1. So let's say logic 0 is 0 and logic 1 is 5 volt. So in like analog world, then you are saying that you can have only two possible values like 0 and 5. Now let's say if you are the output is connected to control the speed of a motor here, right? So since you are can supply only two voltage levels like 0 or 5, it's mean that either your motor will not be running at all, or let's say it will be running at maximum speed. So there will be nothing in between. Like let's say if I want to say it's, I don't want to run it at the maximum speed, I want to like slowly increase its speed from like let's say 0 up to maximum, and then again to 0, and then want to increase again 0 to maximum, right? So I can't do that. Why? Because I can generate only two voltage levels, either 0 or 5 on the output. I cannot generate anything in between like 2.5 or 3 or 4 or something, right? So that's why I first need to convert the output which is generated by the microcontroller into the analog form, and then convert it, connect it, make it as an input to the motor, right? So how can we connect a DAC, digital to analog converter, to AVR? So this is a example of a DAC module or DAC chip. So you have 8 input pins like D0 to D7 digital inputs. So they are coming from AVR microcontroller. Let's say you have 8-bit ADC, right? So the 8 pins, they will be output of the AVR microcontroller, and you will make them input to the your DAC, right? And then these are control signals, write, read, and then here it will provide you an analog input, analog output. We are not going to the internal of this chip, like how it works. We don't care about that. For our purpose, it is sufficient to know that you can actually uh, interface or connect a DAC chip with your microcontroller to calculate the or to get the analog signal. So actually the signal that is generated output on the output, it is voltage here, analog is voltage, but then you can convert it into the current by converting by connecting it with some resistors which we are not going to see here. And how that is output current is calculated using this equation. So what we have in this equation, so IREF, this is reference voltage, sorry, reference current, and then the value depends upon the value of the output current depends upon your 8-bit input. So this input here, 8-bit input coming from your microcontroller. So So for example, if all the bits are zero, all the 8 bits are zero, the output current will be zero. But let's say if only this bit is D0 is 1 and all other bits are 0, then it will be IREF times 1 over 256. So actually you are just depending upon the value of these bits, your current value will increase or decrease, right? Any questions? Okay, so let's go to quiz number 13 then. Okay, you have 60 seconds. Okay, we can have 15 more seconds. Okay, I don't have a solution for that, but it is straightforward, right? You just need to plug in the bit values and you will get the uh, I out or output current. Okay, so we can at least start this topic and we can continue next week then from there. So topics we are going to cover here are little Endianness and assembler directive, right? So what we mean by little Endianness? Oh, story. Yeah. So let's say you have this number, data, 8-bit data, right? 0xF4CD042A. So 2A is your least significant bit and F4 is your most significant bit, right? Now, let's say we have memory and the lower row shows the memory addresses 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the upper row actually is used to indicate the data that is stored at that particular address, right? So the question is that how should the data be placed in memory, which means that if we want to place this data in memory here, how should it be placed, right? There are two options. First option is like which is known as little endian. So don't get confused by the name. So but the first option is that you can start by placing LSB of the data in lower or starting address. So let's say if your starting address is 2, right? So you can write this data into the memory starting at address 2, but first putting the least significant bit. So this is your address 2. You first put the least significant bit, which is 2A, right? Then at address 3, you put the next byte, which is 04, right? And then at the next address 4, you put the next byte, which is CD. And then at the next address 5, you put the next byte F4, right? So here the point is that your least significant bit, you start putting the data in the memory starting from the least significant bit. So least significant bit has the lowest address, right? And most significant bit has the highest address. So the C2A has the address of 2 and F4, which is the most significant bit, has the address 5, right? So this is known as little endian. So you start from the little side, the least significant side, to put the data in the memory, right? Other option is that when you are putting the data in the memory, you can start by placing most significant bit first in the lower or the starting address. So for example, if we do exactly, we place the exactly same data, but using the option 2 or the big endian. So first we will place the most significant bit. So if our starting address is same 2, so first we put the most significant bit, which is F4, then the next relatively least significant, less significant bit CD at address 3. At address 4, we put 04, and at address 5, we put the least significant bit 2A. So in big endian, what happened that your most significant bit goes into the lowest address and your least significant bit goes into the highest address, right? So this is known as big endian. So actually the question is like, from where should your least significant bit go? So one option is that we put the least significant bit in the lowest address or at the starting address, and the other option is that we start putting the data in the memory from the big side or most significant bit side, right? Is everyone clear on this? Any questions? Okay. So this little Indian approach of like putting the data in the memory or reading data from the memory is used in chips like Intel x86, x86-64, Atmel microcontrollers, and Bing Indian approach is used by some other chips, for example, Motorola 6800 and 68K, right? So let's have a look at this example now. Let's say you want to read four. So this is like situation condition of the memory. So you have memory from zero address 0 to 0 to 9 shown in the figure, and you have data already placed in the memory at address 2, 3, 4, and 5. Now your job is to read 4 bytes from memory starting at address 2, right? Using little endian placement. So you now need, let's say you need to read these 4 bytes and need to put in a 16-bit register. So what I'm asking you is that what will be the content of the 16-bit register if you read 4 bytes from the memory starting from the address 2, right? So this is your next quiz. So we have like, I think 1 or 2 minutes. So let's try doing this quiz. I think I made mistake. Should be quiz 14, right? Yeah, yeah. So let's see what is the result. So result will be, see, we need to read out from the which side, from the least significant byte. So which mean that first byte that we will be read will be the least significant byte, right? Because it is little endian. So it will be 2A. The next byte that we will read will be the uh, second least significant bit. So which will be 04. The next byte that we'll read will be the third least significant byte for which is CD. And then the last byte that we will read will be the most significant byte, which will be 0xF4. Is everyone clear on this or not? Okay. So we are actually running out of time. So our time is over. We can stop here, and next time we can start from the same place, and we can actually redo this example so that we can have everything fresh in our memory, and we can start from there. Any questions before we leave? No? Okay. So if no questions, then that's all for now. And thank you. See you. Yeah, you have the lab. So do your labs and see you on Thursday.